Hello, welcome back to Chemistry 131. Let me dial the music down here. So, on Wednesday, the college was closed due to a windstorm. And I intended to have this lecture up on that evening, but due to circumstances with the internet and then plans to try and upload these faster, I ended up wasting time, ironically. So, this is the first time that I've kind of had a moment to sit down and actually do the lecture. So, this will be going to YouTube on Friday night, which is the 15th. This is intended to be for Wednesday of week 2, as you can see at the bottom. We're going to cover the rest of the content in chapter 12 that we didn't do on the previous lecture day, which was Tuesday. All right, so we're going to talk a little bit about how alkanes can be used in chemistry. Hint, they can't. We can blow them up and that's it. We're going to talk a little bit about how we can halogenate things. There are reactions that make these halogenated hydrocarbons. We're going to talk about in the next chapter, in chapter 13, when we get to alkenes. And we're going to talk about cycloalkanes, because we've been talking about linear stuff where all the carbons are just in a row so far. But what happens if you loop them around back on themselves? Can you make like a circle or a shape or something like that? And it turns out you totally can. And there are some interesting consequences of doing that we're going to show in the model viewer. Okay, so I gotta find my pen. There it is. Let's go ahead and get started here. Alkane chemistry is actually very boring, only because there's like one reaction that we care about, and that's combustion. That said, combustion is extremely important. You use combustion all the time. When you get into your car and you drive around, what your engine is doing, it is combusting an alkane. Mostly heptane, some octane, and then we add in other stuff in there, like ethanol. We used to add other more complex molecules. You might have heard of like leaded gasoline, and now we only allow unleaded. We used to put more complex stuff in there, and there's a variety of reasons for that have to do with like keeping the engine running at an appropriate temperature and force, so like you don't knock the engine, which could cause damage, etc. I'm not an expert on like how an engine works. I just know the chemistry of the reactions that go in there. Now, whenever you do a combustion reaction, one thing is required to, well, I guess there's two things because there's two reactants, but specifically when you do a combustion reaction requires oxygen. Okay, so whenever you have a combustion reaction, oxygen must be involved somehow. Now, if you are combusting an alkane, what that means is that you are reacting some sort of substance that has some carbons in it and hydrogens in it, and then we said that was this. I put X instead of N, but that's okay. You're going to react that with oxygen, and there are only two possible products that come out: H2O and CO2. Now, I didn't balance the equation because I don't know what X is. And you could theoretically balance it, I suppose. So, like, I could put a variable in front of, like, I would make X CO2, and I don't know how many water I would make. I don't want to do the calculation. It'd be like X plus 1 or something. And then how much oxygen do I need? Pfft, whatever. It's algebra. We could do algebra if we wanted to, but I promised you that we wouldn't. So I'm not going to do that. But these are the products that you get specifically when you combust any alkane. Now, this is called complete combustion because we are completely consuming the alkane with abundant oxygen. That means that I have all the oxygen I could ever want. Now, when I hit a button, it's probably going to appear over this, yeah. So, on this example, I use pentane. I didn't do another example, but the important part for doing this is that you get tons and tons of energy out. These reactions are very exothermic. They release energy, and that energy is then used to perform work. So, for example, when you combust the hydrocarbon in your engine, it creates an explosion, and that explosion pushes the piston back in the engine, and that piston is connected to other things like crankshafts and eventually your axles and the wheels and etc. And so the energy of those little explosions going off repeatedly is what causes your car to move forward because it is being pushed by those explosions in the car engine. Now, what happens if we don't have enough oxygen? So, for example, let's suppose that you had a fire inside a container and like it started consuming all the oxygen and there wasn't enough left. You wouldn't get CO2 and H2O because there isn't enough oxygen to go around. Typically what happens is that this O in CO2 doesn't quite fill in all this. We don't get enough O to make CO2. And so we end up making our CO or C. So you've probably heard of this before. This is carbon monoxide. Carbon monoxide occurs when you have incomplete combustion. And carbon monoxide is very bad. It's called the silent killer for a reason. And that reason is you can't smell it because it's odorless. It's colorless, so you can't really observe it. And also, what ends up happening when you inhale carbon monoxide is that it binds pretty much irreversibly to your hemoglobin. So the iron, which is supposed to carry the oxygen in your bloodstream, or in your blood cells, instead gets carbon monoxide bound to it. It's very difficult to get that carbon monoxide off of the hemoglobin, and so what it basically does is it ties up sites that should be carrying oxygen to your cells. Since you aren't getting oxygen to your cells, what you slowly do is you asphyxiate. And so when you breathe too much carbon monoxide, what you end up feeling, at least this is what I am led to believe. I've never breathed carbon monoxide to the point where I've passed out, but you just basically get sleepy and then you die. So please do not do things like barbecue indoors, because that is a very common situation where this can happen. If you have like a propane grill and you're grilling in, say, your garage because it's cold outside, you may use up too much oxygen in the room and then asphyxiate because you start creating CO. So never do any sort of combustion reaction indoors where there isn't enough oxygen unless you have adequate ventilation. Things like your fireplace are vented such that all of the smoke would rise up into the chimney and out of your house. And by doing that, you create a sort of positive pressure where I don't know if it's positive or negative, but anyway, with the air going up the chimney, air has to come in from other places to replace that air that is moved. And so generally that would be like through your windows or under the seams of the door or etc. So you would have airflow going through your house and up the chimney so that any CO that was produced in the combustion of firewood would not asphyxiate you. But if you close the flue on your fireplace and the smoke goes into your house, you will just quickly get smoked out, and that's very bad. The same thing if there is a fire and you are trying to run through it, like your house is on fire and you're trying to escape, like breathing any of that smoke is very bad, not just because of the CO, but particulates and other stuff. So make sure you are combusting correctly, I guess, is my advice there. Other than that, most chemicals don't really react with alkanes. There are some reactions that can, but these require very specific conditions. So, for example, we need like UV light to do halogenation reactions. That's what this is. This is not the reaction that I am going to require you to know to do a halogenation reaction. A halogenation reaction being a reaction where you produce a haloalkane, which is what we're going to talk about in the next section. Sorry, I'm just drinking water here. These are just fun facts. According to your textbook, and I don't think that I knew this, I knew that iodine was not very reactive because it's just so damn big. Fluorine apparently is very explosive when it comes into contact with alkanes. I didn't know that. Generally, when you create fluorinated alkanes, you get a very stable product. So that does check out now that I'm thinking about it. A particularly stable fluoroalkane compound would be something like Teflon. So if you have cookware coated with Teflon, that contains fluorinated alkanes. So that has haloalkanes. But I don't know the process by which Teflon is made off the top of my head. I expect that it does not involve explosions because otherwise, like, the sacrifices we would have to make to create cookware would be a little bit extreme. We're going to make chlorinated and brominated and iodated haloalkanes by a much simpler mechanism using alkenes in the next chapter. And so we'll go over that when we get there. All right, let me get some more water, just a second. My seltzer is all flat because I spent a while preparing for this. Let's talk about how we name halogenated alkanes. So haloalkanes have a lot of common names, but we are going to stick primarily to IUPAC names. What that's going to boil down to is that we're just going to have a bunch of groups that we give more names to. So like we had the methyl group before, or the ethyl group. Now we're going to have the chloro group. What could the chloro group have? Maybe it's chlorine. Yeah, like this is basically just, let's name alkanes part 2. Hooray. So here are the new names for the groups that we're going to be adding. We got fluoro, chloro, bromo, and iodo. Honestly, the only important part about that is you just need to know how to arrange them alphabetically. Because remember, when we name stuff, after we do all the numbering on the chain and identify all the groups, we need to we need to arrange them in the name alphabetically. So you're going to put bromo before chloro, before fluoro, before iodo. And then you're going to have to stick like ethyl and methyl and isopropyl and all of that in there too. Now, I'm not going to test you on common names. So you may have heard some common names for haloalkanes, such as maybe methyl chloride or methylene chloride or chloroform. Those are different haloalkane versions of methane where you start substituting out hydrogens on CH4 for chlorines. You don't need to know those common names. I'm not going to ever use them on the exam. You can always look them up if you want to. We're going to stick with entirely systematic names. So let's do an example here. Since you have already done the naming section, what I want you to do is pause the video and try and name this based on what you think the naming rules are. And you're going to be surprised that it's going to be exactly the same, and you're going to do just fine. So number it based on what we said the rules were. I'm going to try and be mum about what those rules are for just a second so that you can try and do this on your own. And then when I come back, which will be like 2 seconds later, so get ready to pause the video, I will go over the answer. Welcome back. I hope you had time to think about the answer. Yeah, it was like 2 seconds for me. So what we're going to do is we're going to first identify the longest chain, just like before. Now, ideally we want our longest chain to contain all of the groups off of it. Because otherwise we're going to have to be naming this with some sort of weird nomenclature. And that's sort of beyond the scope of this class. So you're not going to see any groups that have groups off of themselves in this class. So keep that in mind. Now, there are a bunch of ways to connect 3 carbons here, and there are actually a few ways to connect 4. I'm going to do this way. 1, 2, 3, 4. That's going to be my longest chain. Now, you could have included the top methyl or even this bottom methyl instead. It would be equivalent. This methyl on the left here, which I'm going to number. I'm going to just put a star here for now. These are all equivalent. So you could have included one of these in your chain, and that would have been fine. The next thing we're going to do is we're going to number our chain. But are we going to number it left or right? What did you do? Remember what our priority is for numbering. We want to number it so that we have the lowest possible numbers going in whatever direction we're choosing. So I'm going to number left to right. And then I'm going to number right to left. And then we're going to compare where the groups are. All right. So let me get the red pen out here. I'm going to circle. Oops, that's the wrong thing to circle. Don't erase my yellow. Okay, good. Actually, let me use the felt tip. I'm gonna go like this. So this is a group, and then this is a group right there. So using the red numbering scheme, I had a group at position 2, and position 2, and position 3. Using the blue numbering scheme, I had a group at position 2, and then position 3 and position 3. Which one has the lower numbers? Well, the top one has 2 2s, and the bottom one has 2 3s. 2 is lower than 3, so this is going to be the correct numbering scheme. So I want to use the red numbers here. So let me get rid of these. We'll get rid of these blue numbers because they're not the numbering scheme that we want. And so let's start naming all the groups. So this is chloro at position 3, so this will be 3-chloro. There is an H in chloro, which people forget. Just be mindful of that. This is 2-methyl. This is 2-methyl. And so now I just got to arrange everything alphabetically. So chloro comes before methyl. So this molecule should be 3-chloro, 2,2-dimethyl. And then what is it? It's got 4 carbons in it in our chain, so it's a butane. All right. Dun da da. Oh, my text appeared over it, but there's the name of it. Now, if you've been following along with how to name these molecules in the previous section, you probably got that right. All you needed to know was what the heck was Cl? What do I call it? Okay. And then again, remember where it goes alphabetically. Something to note, don't include di in your alphabetization. Chloro comes before methyl, so that's why we arranged it that way. Even though chloro does come before the D, if we use something else, the order would still be the same. All right, let's do more of these. Hey, I wonder what this one's called. I don't know why that... we're going to go like this. Give me a second. So this will black out. I'm going to hide the answer, even though the answer was already there. Sorry. Okay, that should now work. So when I go like this, you shouldn't see the answer immediately. Whoops. Technical difficulties. That's okay. I'm going to do the same thing. I'm going to give you a second to try this, and then we'll go over the answer. So hit pause whenever you are ready, and unpause it when you have got the name. All right. Let's see how you did. We're going to do the same thing. We're going to number the longest chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. So I just sort of like count along all the possible branches to see how many I can find. So if I do this, 1, 2, 3, 4, 5, 6. So that's 7. If I started up here at the top, 1, 2, 3, 4, 5, 6, going to the left, 1, 2, 3, 4, 5, 6. Those are both shorter. So going straight through the middle is the longest chain. So this is going to be a heptane of some sort. I mean, of course, we know that because we saw it on the answers when they popped up. And so, which direction do I number it? Well, if I go 1, 2, 1, 2, 3, going left to right, or right to left, the first branch occurs at 2, going left to right, whereas the first branch occurs at 3, going right to left. So we know that that must be correct. So let's keep numbering. And now I'll just start naming them. So this is 2-methyl. This is 3-bromo. This is 4-ethyl. And then this is 5-iodo. And now we just have to ABC them. And this is the part I'm bad at because I don't know my ABCs. So A, B, C, D, E, F, G, H, I, whatever. There we go. So I'm going to put the name down here because it won't appear over it. So 3-bromo. Crap, what's next? E. Okay. I'm really bad at alphabeting. 5-iodo, 2-methyl. And then what was the 7? So that's heptane. All right, and then when I go da-da, it should match what I have down below, and it does. Look at that. It's almost like I know what I'm doing. Which is kind of touch and go when I teach this class sometimes. I'm like, oh shit, how do I do this again? Oh, that's right. Because I learned it so long ago. I believe that the next slide is just the examples. Yeah, here you go. So what I want you to do is, now I'm going to give you a name, and I want you to turn it into a structure. So draw the structure using this sort of notation that you can see down here. I can't even see my cursor, so right here. Draw the line angle structure of 5-bromo, 1-chloro, 2,2-dimethyl hexane. And then I want you to name these. So over here I have what I like to call, like, I don't know, I'm just making these names up on the fly. This looks like a ballerina, like, balancing on a foot. And, like, this is her a hand, and this is another hand, and this is her head. Don't tell me why her head and her hand are the same. Like, and then over here I have, like, this sea turtle, or sea creature of some sort. I just draw these because they look fun. So there's no rhyme or reason why I have these specific examples, but they make for good practice. So try and name these, and we'll go over the answers together in just a second. So pause the video, and I'm going to take a short pause to get some more water too, and then we'll go over them together. Jeez, I'm sitting here talking, and I forgot to unmute. Let's try that again. Okay. I don't know what I'm capturing. Yeah, there we go. So let's start. Ooh, that's not what I wanted. Hold on. You know, I never moved this, so let me lock Photoshop in place here. There we go. Now I can't accidentally move it anymore. Oh, that requires me to actually click on Photoshop. Sorry, I'm a spaz tonight. Okay. I personally find turning a name into a structure to be a lot easier. And the reason for that is because you can basically just draw the chain. So I know it's hexane, so what I'm going to draw is a hexane chain. There's a hexane, right? And then I'm going to number them left to right. So this end's going to be 1, and this end's going to be 6. I'm going to just put stuff in as I see it. So 5-bromo, 1-chloro. So I could go in any direction. This is fine. 2,2-dimethyl, 2,2-dimethyl hexane. There you go. We'll get rid of this number 1 and this number 6. Now, a common mistake that beginners make, and I know this because I constantly did this all the time, was that they add extra carbons in when there aren't any. So this point right here is a bond to chlorine, but for some reason when I'm starting out to look at these, I always think, oh, maybe that's a carbon, but it's not. Okay, so carbons are only at vertices or endpoints if there's nothing attached. So I'm gonna put little blue dots down to let you see where all the carbons are. And then what I'm going to do is I'm going to circle our hexane here. There you go. So there's our hexane. And I guess we'll number it too. I mean, more information is good for you guys, right? Like, I'll just, whatever you need, I could just put it on the screen. That's totally cool. So there's the structure for 5-bromo, 1-chloro, 2,2-dimethyl hexane. Now, if you are ever unsure of how to draw the structure, you can research this, but what you'll definitely note is that oftentimes you end up getting a conformation. So remember that a conformation is just a different way to draw this molecule. So instead of drawing it like this, what you in like a linear fashion, what you might end up finding would be something like this. So 1, 2, 3, 4, 5, 6, and then here's Cl, and then I've got this going on, and then I've got this going on. So this is the exact same molecule as what's drawn above, but at a very quick reference, if you were to just look at this really quickly, you'd be like, oh wow, I did it totally wrong, where in reality it's totally fine. Other issues that can come up, and this is just something that I'm going to play with here. How do I free transform here? There we go. Like, maybe your molecule looks like this instead, or like that, or can I invert this? Flip horizontal. Yeah, there you go. Now, obviously, I can't preserve my my handwriting here because I'm rotating this and bop it, twist it, turn it, pull it, whatever. But any of these orientations results in the same molecule, but a different appearance. So be kind of careful when you are looking up answers on Google, because who knows what conformation the molecule is going to be in. But if you can take their conformation and untangle it so that it matches what you drew, then you can use that to check your answer. You can also build stuff on MolView. There is a search function that you can type molecules into, but I don't think it's exhaustive. So if you typed in this molecule, I'm not sure if it would be there. You would have to try it. That's really all I could say. Okay, I gotta get this dotted line off my screen there. There we go. And then I need to do this. There we go. Actually, you know what? We could do that on this page here. Or we could just skip everything. That's not what I intended to do. There we go. Sorry, I'm clicking around here and then everything is falling apart. Pen. Okay, so let's find the longest chain. Now, I want the first branch to occur on the lowest number. So obviously 1's going to go over here because this is the first carbon and I've already got this fluorine coming off of it. If I put 1 over here or 1 over here, the first branch wouldn't occur until 3. So I know where the starting point is, and we're going to number it from here. So this must be 2, this must be 3, and then no matter which way I go, I'm going to get the same result, right? So just to be contrarian, I'm going to go like this, so that we're not always just going left to right, because that's not always the answer. Let's name our groups. So we've got 1 fluoro, 2 fluoro, and then at 3, I have this chloro here, and then here I have 3 ethyl. That's this group right here. And then we arrange them alphabetically. So chloro comes first, so that's 3 chloro. And then E is next, so 3 ethyl. If you have 2 groups that are connected at the same position, yeah, you have the same number twice. That's fine. We got 2 fluoros, so I have 1, 2, difluoro. Don't forget this U in fluoro. And then what is this? 1, 2, 3, 4, 5, pentane. There you go. Let me just erase this mark here. All right, over here, this is a little bit crazy. Where's my longest chain? So I'm just going to number stuff. So let's try this to start. So I can go 7 that way. If I go up, that's only 6, and I have a bunch of stuff down here. So this is obviously not right. But if I branch from 5, I could go 6, 7, 8. That's longer than 7, so that's good. Is this the fastest way to do this? And because the molecule is symmetrical down this, like I made it a mirror image of itself. Numbering it either way, you're going to get the same thing. So let me tidy up here. So let's get rid of these here. I want to keep that 5, actually. So you can number it left or right. You'd actually get the exact same thing. So let's number the groups. So, oops, I gotta go down here. So 3 bromo, 4 ethyl, 5 ethyl, and then 6 bromo. And so this one will be called... I was going to write down here, but now I'm kind of far apart, so... Well, you know, you could just pause the video and go back if you want this answer again. So we're just going to get rid of this guy. So I have enough space because, let's see here. So bromo comes before ethyl, so 3,6 dibromo. And then 4,5 diethyl. And then that's all the groups. So that one, that one, that one, that one. One of the other have an 8 is an octane. There you go. That's how you name haloalkanes. Just like you name any other alkane that we did before, but now you just have a few more groups, so I can make more complex molecules that you get to play around with. Okay. Any questions, let me know. Send me an email, drop by the Discord. I'm happy to go over these examples with you. All right, now we get to go to the fun stuff. What happens when you make a circle? You get a cycloalkane. Woo! Now, cycloalkanes are basically like linear alkanes, but they loop around, and they have minor differences with them. So, like, for example, instead of naming it hexane, we would name it cyclohexane, because it's a cyclohexane. No big deal. But how the hell do you number a ring? Like, where do you put 1? And it turns out that the same rules that we've been using apply. Number them in such a way that you get the lowest possible number. So something's always going to be 1, and then you go either clockwise or counterclockwise based on whatever gets you the lowest possible numbers. So the rules still apply. It's just you have to think a little bit about how you will apply them to these. Okay? So on the screen here, I have propane. And I'm going to write its formula based on what we count. So this is C3. And you probably know that this would be H. 2 times 3 plus 2, which is 8. 3, 6, 8. Cool. Over here, I have cyclopropane. And it's still C3 because it's cyclopropane. But how many H's are there? Well, there's only 6 here. So the formula for cycloalkanes is this, CnH2n. And the reason that there are fewer hydrogens is because I have used one of the bonds on this carbon and one of the bonds on this carbon to create a connection between the 2 carbons. In other words, I took away 2 hydrogens, leaving an unpaired electron on each carbon, and then I bonded those 2 unpaired electrons together to make the cyclic structure. So in order to do that, I had to remove H2. So instead of H2n plus 2, like this was how it was for alkanes, we just get rid of this part so that we can complete the ring. All right, and there's our formula again down at the bottom. So cycloalkane is any alkane that contains a cyclic CH structure. Now, an important caveat of this is that there's only going to be single bonds in our cycloalkanes. If we have double bonds present, that's different. We're going to get to that in the next chapter. Those are called aromatic compounds. So, single bonds in cycloalkanes only. I went off the screen there. I apologize, but it says cycloalkanes. Now, just like before, we're going to number the chain. The chain is a circle, and in some cases, it's actually not even worth numbering, because if there's only one group, you're always going to number it with the lowest possible numbers, right? And the lowest possible number will always be 1. So if I give you this, and I say, name this, well, this is always position 1, so it can never be anything other than 1-methylcyclopentane. So why even include that part? So if you have only one group coming off of a cycloalkane, you just put the group name, and you ignore numbers. Because there's only one possibility, right? If you have more than one group, then you do need the numbers. So let's look at a situation where you do have that. Now, we're going to have to number them so that the lowest possible numbers occur. So what that means is we're not going to do this, because that would put my groups on 1, 4. Instead, we're going to do this, 1, 2, 3. And so my groups occur on 1 and 3. But wait a second. What if I did... Oops. What if I... Oops. Yeah, there you go. What if instead... That's not the pen. There we go. What if I did this instead? I mean, in both directions, I get 1, 3. What the heck do I do there? The tiebreaker is alphabetical. So if you go in both directions and you get the same numbering result in both directions, you give the lower number to the one that comes first alphabetically. So in this case, that'd be chloro over methyl. So I don't want to erase all. I want to just erase these guys. So lowest numbers on groups. And then we'll break ties using alphabetical. Okay, so let's name it. So I'm going to try and put the name somewhere where text won't appear over it, but I have no hope that that will happen. So 1 chloro, because that's what this is. And then 3 methyl. And then what is it? It's got 5 carbons in a ring. It is a cyclopentane. I don't know if I can fit the text here, so there we go. There you go. That's the name of it. 1 chloro, 3 methyl cyclopentane. So let me clear my text here because it's going to then go through the process. There you go. I put in all the numbers 1 through 5 just to number the entire chain. You don't need to do that. It's like this 4 and this 5, this is not helpful. You could number it to be complete if you'd like. It's totally up to you. Let's name this one. Now, again, we could go in either direction. We could go clockwise, or we could go counterclockwise, like so. Which one's correct and gives you the answer that names this alkane? I'm going to hit mute for a second to give you a moment. Pause the video, and then when I come back, we will go over the answer. All right, I'm back. I'm doing this thing with my water where I actually have frozen grapes in it, and so I'm eating the grapes, and I don't want you to have to hear me eating the grapes. Like, I can quickly drink the water, but I also want to eat the grapes, because grapes are delicious. So hopefully what you did was you said, okay, well, if I put the 1 on this CH3, that's methyl. If I put the 1 on this group, that's bromo. So bromo is the first alphabetically, so we're going to go in this direction. Now, in a second, we're going to do a different example where I'm actually going to just switch around some groups, and we're going to see what the name of that would be. But for now, this is the correct orientation. So this is 1 bromo. This is 2 chloro. And this is 3 methyl. And so this would be... Those are already in alphabetical order. So I'm just going to go... I'll write the name down here. 1 bromo. 2 chloro. 3-methyl. And then this is cyclobutane. There you go. Do. But now what I'm going to do is we're going to go over here. And I'm going to make this just really small because we don't really need it for my sample problem. I am going to draw a molecule. In fact, you know what I can do? Hold on. Let me get ChemDraw out. Where is my ChemDraw? Let me make the structure in here. Boop. And then I want to do that and that. So I want this one to be bromo and this one to be chloro. Ah! Sorry. I hate that sound. That happens if I hit the wrong key. Paste. That wasn't very good now, was it? I need to make this bigger before I copy it then. Okay. Copy, paste. That's better. Okay. Did that put that on another layer? No, it didn't. Okay, that's the right layer. Okay. How do I name this one? Because now what we're going to do is we're going to try and number them. But there's going to be a specific temptation here. And that temptation, so this is methyl. This is bromo. And this is chloro. How would you number them? I'm going to give you a second to come up with the answer on your own. And then I will tell you the correct answer. Apparently there's a fire or something going on my street, because there's a ton of fire engine sirens going on. Anyway, let's go over the answer before everything burns down. How did you number these? Did you start here? Because, hey, bromo, I got to make sure that it has the lowest number. Because if you did, then you're going to notice that what happens is there's no way to get 1, 2, 3 going around this, because the groups would be at 1, 2, 4. Remember that the lowest possible numbers need to be assigned. Okay? So what that means is that the only way that we can do that is we start at the chloro or the methyl. Chloro comes first before methyl does. So I'm either going to number from here is 1 or the methyl is 1. Chloro comes first and alphabetically, so it gets the 1. Bromo can never be 1 if the if the groups are arranged in this orientation. Because the best I could do would be 1, 2, 4, numbering it that way. Okay. So this molecule as drawn would then be 1. Oops, sorry, I missed bromo here. 2 bromo, 1 chloro, 3 methyl, cyclobutane. And then if I make this bigger, you can see that the only difference in the name from the previous problem, which you kind of can't see because part of it got cut off here. And the problem that we just did is that all I changed are the numbers, right? So this number right here, and this number right here, and this number right here. Well, actually, the 3 stayed the same. But the 2 and the 1 are all that changed in the name because we're arranging it alphabetically, right? So that kind of checks out. And these problems make sense in retrospect, but there is definitely a consideration that when you're starting to do these problems, you want to look at this and go, man, I really want to call this one 1. How do I do that? And the answer is you can't. So be careful that you don't try and do that. Number the chain, and then you got to go along the chain. All right. So I'm going to give you 2 more molecules to name. I'll pause the video, or I'm sorry, you will pause the video. I can't pause your video. I mean, I could do all sorts of crazy stuff over here, like whee, but I can't actually pause your video. So you do that. Give the names of these compounds, and then we'll go over the answer in a few minutes of your time. I don't know, whatever you choose. Whenever you hit play, I'll be back here. So see you in a bit. All right, I'm glad that you came back because it was starting to get a little crazy out here. The fire engine stopped, but I don't know what that means. I don't see any flashing lights outside my apartment. This is kind of what I imagine like the apocalypse would be, like the world is falling apart outside and here I am teaching. On this first one, there is only one group, so we don't even need to number it. We just need to identify what it is. What is this? That's an ethyl. Cyclopropane. Over here on this one, I need to either number starting at the methyl group or the chloro group. Chloro is first alphabetically, so we're going to number it in this direction. 1, 2, 3. And so this will be 1 chloro, 3 methyl, cyclohexane. There you go. Easy as naming alkanes, I guess. I don't know. Now, you might not think that there's much else to this. Like, we named chloroalkanes in the last section really quickly, and now we've named cyclochloroalkanes, and that's easy. And it turns out that due to how geometry works with alkanes, all the carbons are tetrahedral, we get some interesting consequences when we hook them around into a ring. And so we're going to encounter an entirely new sort of isomerism here that's going to require us to look at stuff in 3D. So that's going to come up in a little bit. I've made some pictures in mall view for this to show you. But let's put more problems on the board. I'm sorry, I didn't realize that those were there. I guess I'll pause or you could pause the video again and draw the structure of these compounds. So I'll see you in a bit. All right, let's go back to this. Oh, I don't even know what's going on anymore. Not with the organic chemistry. The organic chemistry is like the only thing I know that's going on. It's nice to have one constant in your life. All right. The purpose of this first problem is to see how well you can draw a 7-sided shape, I guess. Here's how I do it. So I start at the top and I go 1, 2, 3, 4, 5, 6, 7. That turned out pretty good. And then I'm just going to pick a position to be 1. I can pick any position I want to. I'm going to pick this one just to bug people. And then if that's 1, then I just got to go 2, 3. I'm going to go counterclockwise. Haha, you can't stop me. Iodo. Cycloheptane. There you go. So that would be 1 ethyl, 3 iodo, cycloheptane. And now, of course, you can have that in any orientation or permutation you want to. So, if you had it rotated around, so free transform, there we go. You could have it like this, or whatever. Like, any of these is fine, right? All right. Isopropyl cyclobutane. Really, the trick to that one is just remembering what the isopropyl group was like. And so we did that in a previous lecture. I want to say it was Tuesday of this week. So there's no number, which means that any of these groups will just be 1, and then isopropyl looks like a Y. Remember that. All right, so hopefully those are the results that you drew. And again, any orientation is fine. Any conformation is correct. All we care about is the connectivity, so as long as everything's connected correctly. All right. There's my geometry. Okay. So recall that whenever you are drawing these carbons in 3 dimensions, the geometry of each carbon is going to be tetrahedral. What that generally means is that if this is my carbon, and I have something pointing up and then something pointing sideways along the chain, something's going to come out of the paper at you, and then something's going to go into the paper away from you. Now, when I start hooking things into a circle, you can imagine that this is like part of, say, let's do my cyclohexane like this. Now I've got something that came out of the paper right here, and something that went into the paper right here. And if I were to just replicate that with any position, the same thing occurs. And so I'm always going to have an into and an out of orientation at every corner of a cycloalkane. We're going to show that on the model viewer in just a second here. Now, what that means is that it becomes important to show the direction that things are oriented. For instance, I'm going to just draw this flat right here. So this is CH3, CH3. And so there are 2 different ways to represent this molecule. That I have drawn. Now, there are actually other orientations, so I could flip them both opposite of each other in the different direction, so the left one goes up and the right one goes down, and then I couldn't rotate that to get it back to look like this one that I've shown here. But these are just 2 examples that I have shown. Remember that every carbon is connected to 4 things. So right here, at this carbon specifically that I'm drawing this big dot on, there is a 4th thing bonded to it, and that 4th thing must be hydrogen, right? So hydrogen must be right here. Likewise, with this carbon over here, the hydrogen goes down. And then over here, I have them going up. Now, these are drawn such that they look like they're 90-degree angles. Remember that these are all tetrahedral. This is sort of just a shorthand to show, okay, when I point this structure, if I were to rotate it out of the paper at you, like if you put your hand against the screen and then you tilt your fingers into it, that would be what you're doing with that molecule. So your hand on the screen is what I drew in red, and then you push your fingers forward so that your hand is now flat ahead of you. That's the molecule, with the groups now pointing up or down. That's the best way I can describe it without actually showing you, unfortunately. But as you can see, what's stopping me from having my methyl groups point opposite from each other or in the same direction? And then more importantly, once I've reached this point, can they change back? Well, we talked a little bit about bond rotation when we were talking about single bonds, and we said single bonds can rotate. But everything that's connected to it would also rotate. So if I was going to rotate around the single bond, then this would move down, but so would this bond right here, and the rest of it's all connected, so it'll all kind of come along with, right? So if I rotate this molecule around this bond, I'm not actually rotating around the bond, I'm just rotating the whole molecule, because it's all hooked together. So the end result is that cyclic bond, not bonds, sorry. So any bonds that are in the cyclic structure, they can't rotate. So this bond can't rotate, this bond can't rotate, this bond can't rotate, that bond can't rotate. What that means is that these groups are fixed in their position. And so this molecule and this molecule are not the same. I can never rotate the molecule on the left to make it look like the one on the right. I just can't do it. Now, if I was going to name these molecules, we would use the same naming scheme as before. I'm going to number the chain, and I'm going to number the chain. And you're going to say, well, wait a second, we have an issue because they're both 1,2-dimethyl cyclobutane, right? Now, this one is also 1,2-dimethyl cyclobutane. So in order to differentiate these, we're going to add a prefix. The prefix goes right at the front. And the prefixes that we're going to use, you've probably heard of these before because this comes up in I'm not really sure how to describe what this comes up in. Politics, I guess, or LGBTQ rights and stuff. Like, I'm a member of the LGBTQ community myself, so I hear cis and trans all the time. And so we know that if somebody is cisgendered, their gender matches what they express. And if they're transgendered, it's the opposite. Cis and trans mean that. So cis is same, and trans is opposite. So we're going to apply that to what we see on the picture. Which of these looks like same to you, and which of them looks like opposite? And so your rubric should basically be, oh, okay, well, these are on the same side, right? So they're going to be cis, and that's what we do. These are on the opposite side, and so they're going to be trans. And so that's how we differentiate between these two molecules. They have the same name, which I wrote in red, but they have very different structures in terms of their geometry. And to differentiate that, I have included the cis and trans label. Our rubric is going to be whether they're on the same or opposite side of the cycloalkane. Okay? Are they both pointed up or are they both pointed down? Doesn't really matter because I could rotate this upside down 180 degrees and then these two would be both on the top. What matters is they're both on the same side because remember, this can't rotate. And so I can't interchange between the two structures. All right, I have no idea what's going to happen. Oh, so I think what's going to happen now is I'm just going to explain this. So there we go. So there's a cleaner structure. My trans molecule here has my groups on opposite sides, and my cis molecule has them on the same side. All right, and there's our names. Okay. All right, let's do a different example here. What would I call this? Is this cis or trans? Or can you think of a different sort of consideration, I guess? Let's write down our group numbering. So obviously everything is at position 1. So I'm going to write this 1,1-dimethyl cyclobutane. Now, do I need to write the 1,1? Turns out, yeah, I should, because it could be 1,2, could be 1,3. If I have two of them, I need to indicate where both of them are. Just writing dimethyl cyclobutane would give me a list of a bunch of different isomers, right? So I do need the 1,1. But do I need cis or trans here? And the answer to that is, well, is there a way to make this molecule cis? Could I get both of the CH3s down here on the bottom? Not if it's tetrahedral, right? One's always going to point up and one's always going to point down. So this molecule can't be anything but trans. So if both of the groups are on the same side, we automatically go, oh, they have to be trans, so I don't even have to worry about cis-trans isomerism. I don't need to put a label on it at all, and so I just put the name of it. So this occurs only when both groups are on the same carbon. You don't even use the labels because you don't need to. They will always be opposite sides from each other. So they would always be what we would consider to be trans. It's sort of the same circumstance as when you had one methyl cyclobutane. You don't need the one if it's always going to be numbered position 1 with only one group. All right. What do we call these? They're obviously isomers because they're different, right? Like, we saw that they were visually different. And so we're going to call them stereoisomers. Now, stereoisomers are actually a family of many different types of isomers. The ones that we are going to look at in these examples that we are looking at right now, I can't spell geometric. They're called geometric isomers because they have different geometry. They might point in the same direction or they might point in different directions. Later on, we're going to talk about chirality and enantiomers when we start talking about carbohydrates. So you're going to hear the term stereoisomer come up fairly often in this class, but the first stereoisomer that we're going to care about are geometric isomers. So that's what we're doing right now. Whenever you apply cis-trans to something, it's a geometric isomer. What a geometric isomer is a molecule where all of the bonds are in the same place for both isomers if you were drawing it on paper. So, like, I could draw two versions of this molecule, right? I could draw one where they're both pointing towards me, or I could draw one where one is pointing towards me and the other one is not. So all my bonds are in the same spots if the paper is flat, right? But these stereochemistry indicators, these wedges, indicate that one is going up and one is going down. So they're not technically in the same spot. They just look like it on paper. So these are stereoisomers. Okay. Now, let's look at some stereoisomers in Model Viewer. Where is my Model Viewer? Okay. So first what I'm going to show you is I'm going to show you cyclohexane. Let me make sure I capture the correct window here. Yeah, there it is. Okay. All right. So here's my cyclohexane. And what I'm going to do is I'm going to rotate this guy up like this, and you can see that there is an up group and a down group for each carbon. But it looks kind of weird because everything is tetrahedral, right? So on this carbon right here that's on the farthest to the right, the up group points straight up, but the down group only kind of points down. Whereas if I go to the next carbon around, the up group only kind of points up, and then and then its carbon points straight down. So they kind of alternate here, right? And so I'm going to just slowly spin this around. And remember, you can go to MolView and create this molecule you want to. I don't actually have it on the screen here, but if you go up to the top here, it doesn't fit. Let me make it a little smaller. You can see up here at the top where I've written cyclohexane. Oops, I didn't mean to click that. You should be able to type whatever you want in there and it'll spit out a structure. All right, so that's cyclohexane. Now what we're going to do is I'm going to substitute in this position and this position. I'm going to have some chlorines coming off of them, and we're going to do both orientations. So this first one is cis-1,2 dichlorocyclohexane. So you can see that I put the wedges on the same orientation. They're both going away from us into the paper. So when I turn this molecule around, both of them should be on the same side of the structure. And you can see that they are, though it does look a little weird, right? So this one's going down, and this second one is also going down, but remember that down for every alternating carbon is only kind of diagonally down. And that's a consequence of how these tetrahedrons line up. But you can see that if I go like this, they're both on the same side of the molecule. It's really hard to rotate these back so you can get them back to lined up. There we go. But if I go to trans over here, and I spin this around, you can see that they're on very opposite sides of each other. And again, you can get these by typing these names in. I actually had to type these names in because when I tried to create them, it made the same model every time. It kept giving me cis, and I didn't know why. But when you type it into the model viewer, these specific molecules are saved in here. So please feel free to go to MolView and explore and spin the molecules around and get a feel for what the geometry is so that you understand cis-trans isomerism a little bit more. Where's my slides? There they are. Okay. All right, so we've already talked about geometric isomerism. So that's what these are. If you can, the only difference between the names is cis and trans. What you have are geometric isomers. So if this is the only difference, then they are geometric isomers. Now, that does not mean that you should just be looking for the word cis and trans, right? You have to have cis trans present, but you also have to have the same name otherwise to get geometric isomers. You're going to see an example where I'm going to try and trick you in a second here. So again, here are our two molecules that we had before, and yes, they are geometric isomers because we just said so, right? Oops. So if I were to name them, this is position 1 and 2. 1 and 2. Excuse me. This is 1. I did a comma instead of a dash. This is a pen. Back. 1. Oh, no, that was right. Sorry. 1,2-dimethyl. Cyclobutane. This is also 1,2-dimethyl. Cyclobutane. And then this one here is trans because they're opposite of each other. And this one is cis. The only difference between these two is the geometric prefix. So these are geometric isomers. But let's look at these two. Are these geometric isomers? 1, 2, 3. 1, 2. So this is 1,3-dimethyl cyclobutane. And this is 1,2-dimethyl cyclobutane. Now, are they opposite or on the same side? So this one's pointing down and this one's pointing up. So these are trans. This one's pointing down and this one's pointing down. So these are cis. So we've got these are different, but this is also different. So these are not geometric isomers. These are constitutional isomers. They have a different structure completely. Oh, I'm sorry. I call them constitutional isomers, but our class has called them structural isomers. They mean the same thing. You might have heard constitutional isomers before. Structural isomers have different connectivity for the same formula. So that was like pentane and then 2-methylbutane. Those are different structures, but they have the same formula. Same thing here. 1,2-dimethyl cyclobutane and 1,3-dimethyl cyclobutane have different structures. So they're structural or constitutional isomers. Okay? So these are not geometric isomers. All right. So what else can we do here? What I want you to do is I want you to try and draw every possible isomer of dichlorocyclobutane that you can. And then what I want you to do is once you have drawn those, tell me which ones are geometric isomers of each other. Okay? So give that a second, and we'll go over the answer together in just a moment. All right, I had to eat more grapes. So I don't know how much space this will actually need. Now, for our purposes, when we care about geometric isomers, we're going to just label them as cis or trans, okay? Now, if you get into really nitty-gritty detail, you will actually see another isomer in here, which I will talk about really quickly, and I'm going to tell you why we're going to ignore that for our purposes, okay? So, first, let's draw cyclobutane. So I'm going to draw it. I'm going to do this structure because that helps us figure out up or down, right? And so I want to do dichlorocyclobutane. To make this simpler, this position in the front is always going to be 1, and this position is always going to be 2, and so on. Okay? So I'm going to do both of them go down. And so this would be 1, 2, dichloro, cyclobutane. And I'm going to go down, up. Excuse me. ClCl. Oops, I forgot my cis here. Because this would be trans. Oops, I misspelled. I didn't really misspell, I just miswrote. That's supposed to be an R. Ah! Steve is messaging me. 1, 2, dichloro. I don't want to put this hyphen here. So this should all be one word. I'm just trying to save on space. Cyclobutane. Dichlorocyclobutane. Should all be one word. And then I'm going to move towards the back here. So this is down, and this is down. And so this would be cis 1,3 dichloro cyclobutane. And then I could have them, sorry, I'm getting really sloppy with my drawing here. I could have them trans. So this would be trans 1,3 dichloro cyclobutane. And then I could do this. What if I did this? Is this 1,4? Well, in reality, if we numbered it like that, that's not the lowest possible numbering scheme, right? So I can't do a 1,4. If I did 1,4, it's actually 1,2. And we've already got both the 1,2s. So that's it for going around on different carbons. There is one more that we didn't do. And that's where they're both on the same one. And so that would be 1,1 dichloro cyclobutane. So you should get 5 different isomers. Now, there are additional geometric isomers that can arise. And what I'm going to do is I'm going to select one of them. You could do this with a different one as well. But we're not going to worry about them for the purposes of this class because we're only going to worry about names. So I'm going to select this guy. And then I'm going to scroll down and I'm going to paste it. That didn't work and I don't know why. Oh, there it is. Come here, you. I need you down here. Okay. So I'm going to take that molecule. And then what I'm going to do is I'm going to draw another one. But I'm going to do it this way. And then my challenge to you is, can you think of any way to rotate one molecule so that it looks like the other? So maybe like by flipping this guy around 180 degrees or spinning it around or something like that. And it turns out that you totally can't. Like, these are not the same. So what the heck do we do? Because if I were to name them, what would be the name of these? And the answer is, well, here's the name right here. We've already named it, right? Oops, I'm on a different layer. Hold on. There we go. Copy, paste. There we go. This needs to go away. There we go. Like, this name works for both of them. So what the heck do we do? And the answer is that we have a... This is where we get into chirality, where these are different structures. They're what are known as enantiomers of each other because they're mirror images of each other. We're going to talk about this in chapter, I want to say it's 16. It's whatever carbohydrates is. But for our purposes, you do not need to worry about this. You just need to worry about whether they are cis or trans, okay? So there are multiple possibilities for trans because these are distinct molecules. I can't spin one around to make it look like the other one. But for any question where I ask you to draw all the isomers, what I want you to draw are just geometric isomers and structural isomers, okay? So draw only geometric and structural isomers. And so when I say geometric, what I mean is I need one that's cis and I need one that's trans, and it can be whichever ones you want. Don't worry about this extra one because this is actually an enantiomer, which we're going to cover later, okay? I realize that that's kind of a weird and confusing thing to add in there, and the only reason I'm introducing it is because later on when we talk about stereochemistry, it's helpful to see it early on, even if I'm not going to test you on it yet, okay? So you're not going to see this for like 5 more weeks, okay? So if you get a question like this, hint, hint, you should get 5 isomers, right? And they should look like this. All right. I think that might be everything. Oh. God damn it, Wes. Whatever. Whatever. There's sound here, so I'm going to just turn this up. And hooray, that's it. All right, that's chapter 12. I'm going to post this lecture on YouTube. It will take a while to process, so I will send an announcement out, and you will have gotten that announcement well before you are hearing this message. So hopefully I did what I was supposed to. That is a future me problem, I suppose. I'm also going to release quiz number 1, which is chapter 12. It covers all of the content that you have seen in this chapter and is worth 15 points, and you get 30 minutes to do it. More information about quizzes can be found in the syllabus, or you can always ask me, or check in the Discord or whatever, okay? Thanks for coming to this extra little makeup lecture that we had. I hope that you found it useful. Let me know if you have any questions by poking me in the Discord or in my email. Send me an email if you need me to. Thanks for watching, and I will see you again next week.